All right, I'm Ismail again. I'm going to discuss with you the parallel and serial data communications or data transmissions. First of all, data is transmission is very important in modern communication system, right? So, and in general, there are two primary methods to transmit data, either parallel or serial transmissions. Uh, Unfortunately, uh, even parallel transmissions looks more faster, but however, it requires additional wiring, uh, increased complexity, cost, and it's also vulnerable to signals interference because of the wire uh, keep close to each other. Uh, in contrast to parallel transmissions, the serial transmission even looks slower, yeah, but actually it is uh, becomes popular because of its simplicity and reliability. And in long distance application, for example, it is more cost effective, less complex. Mm, and of course, it is the viable alternative to parallel transmissions for a wide range of applications. There are a lot of applications now using that serial communications, either USART, yeah, GSM based on USART, Wi-Fi based on USART, GPS based on USART, satellite communication based on USART. Um, then a number of IC or devices that connected to each other based on the what we call the either I2C or SPI, serial peripheral interface, or sometimes it based on the we call one wire communications. All of them are the serial emissions. But there are a few applications that still rely on parallel emissions, such as the uh, parallel printer, yeah, and some of them also are using that. But that's but it's become rare. So when we talk about USART, and USART stand for USART U Universal Asynchronous Asynchronous Receiver R, and T for transmitter. This is what you use serial communication protocol that a lot of is in use, and it can operate in two modes, either synchronous communications as shown, right? As shown, say time in diagram of that. So the data for here in this case now, the data is sampled at uh, the transitions of the clock, positive and negative. So you can see, or we call rising edge and positive and falling edge. Okay, so the data trans, so the data actually is sends with a clock signal alongside a clock signal. So that is synchronous communication. In other words, the data actually is synchronized by the clock. By the clock. The other one that we have is asynchronous communications, which the data actually sent by the format zones or in figure 2. As you can see that from the idle state or status, then it start with pulling down that the the lines that we know as the start bit, then proceed with the data. Example here 11001010, and then append with the parity bits, which is optional, and in short distance communication between the example processor to the computer. We not use priority bits, but sometimes we use the priority bits for error corrections. And then comes the stop bits, and then before the line become idle. So that is asynchronous communication. So what we can see here, the synchronous communication uses say clock signal for precise synchronizations, enabling higher data rates. Example is PI, ITC, and so on. And the clock said means the similar clock used by the transmitter and receiver, and normally the master the ones that generate the clocks. Then the asynchronous communications not depends on clock signals, but it relies on the agreed transmission parameters like baud rates, uses start a stop bit, the size, 1 bit, half, 1.5, 2 bits, for example, and then maybe the priority, right? The scheme, the priority scheme use maybe even or odd, and etc. And then this is some terminologies that's very important for us to understand. MSB stands for most significant bit or least significant bit. Right? Since data is transmitted, right, bit by bit in serial communication, it is important to determine which bit to send first. Right, but most applications, the less significant bit is transmitted first. Right? So we can see that. So 1 1 0 0 1 0 0 mean the most significant bit, for example. So actually it is when we read from the higher most significant bit to lowest significant bit is 0 1 0 1 or 5 0 0 1 1 or 3. Oh, this is 5 3, right, in hexa. Another thing that is simplex communication, which is data can only be transferred from transmitter to receiver and not vice versa. That is simplex. Half duplex communication means the data can be transmitted, right, either from master to slave or slave to master, but not both at the same time, right? But not both at the same time. In the middle, I represent it with the switch block. So once it is connected to the transmitter, transmit lines, then the other sides at the receive lines, right? So only one communications at a time. So that is half duplex. And full duplex means the data can be transmitted from the transmitter to receiver or from the master to slave, right? In at the same time. Another thing that we need to know is about rates, defined as speed of data transmission in bit per second. There is another things, another definition. We call it as, sometimes we call it baud per second, baud per second. Baud rates, baud per second. It can be baud rate also can be the symbol. So the symbol consists of, we need to know number of bits, but for the serial data communication is 1 bit. So we can see that bits per second, right? But for symbol per second means it depends on if that line for example, if we transmit the forgot that one, what you call that one, the communication. You see, we transmit 4 bit at a time, right? At a time. So this in term of symbol maybe it is 1000, but in term of bit it is 4000, right? Because we multiply with 4 bits. Common baud rates include 9600, that normal used by the JFSAM, GPS, and 115 right? You can speed up your transmit baud rates or transmission rate to 115 depends on the device that you use. But whatever it is, right, we need to set the baud rate correctly. Each else the data will not be captured at a time. There is a missed data and data captured. So that we know as the framing error. So baud rate is defined as f clock over u divide, where u divide is a value or divisor of the USART configuration register, and the clock is the clock frequency of the system or the USART itself. Right? Data bit number of bits representing the actual data in each frame, commonly 8 bits, standard ASCII character, but can configure to 7, 9 or other values as needed. Another thing that we have the priority bits is an additional bit included in data transmission to provide simple error detection. Right? So we have even parity. The parity is set to 1 if the number 1, the parity is set. And it's not set, and we can say that the parity bit is 1 if the number of ones in the data is this is wrong here. If the bits number of 1 in the bit is even, right? Is even. So, the second one is odd parity. The parity bit is set to 0 if a 1, if number of 1 in the bit is odd. It's odd, not even. This is wrong. This is wrong. When data is received, the device checks every parity to see if it matches the expected value. If it doesn't match, there was an error during transmissions. So basically, we can see that these parity bits for error detection, is enough for simple applications, and it is reported that most 1 over 10 power of or 10 power of minus 6 error rates means 1 in 1,000, 1 in 1,000 for the data single bit change. Stop bit they signify the conclusion of the data frame. It can be 1 stop bit, 1.5 stop bit, or 2 stop bits. And then we talk about the flow control. So there are flow control. Sometimes we use flow control in our applications, right? So we have two types: hardware flow control or software flow control. In hardware flow control, then we use the RTS, request to sense, and CTS, clear to sense, to control the flow, right? So using and software flow control, we use S on, S off. S on, S off is unit taken 0x E0 and 0x0E. If I know a second, that is known as S on, S off. So we send that character before we transfer, and we transfer. When the receiver buffer is nearing full capacity, it sends the S off character to stop transmissions. So it sends 0x0E, for example, and then S on character is used to resume its one space is available. So that is S on, S off is a protocol that we use in survey flow control. I did use it when I studied the transmission signal between two computers during my C language programming. Pros and cons hardware flow control. Advantage: efficient for high-speed data transmissions, reduces CPU load, and so precise control over data flow with minimal error. Disadvantage: require additional hardware pins and is limited by hardware design compatibility. Software flow control, no needs for extra hardware, offering flexibility, and ease of integration in software. Disadvantage: increased CPU overheat and may not perform as well in high-speed data transfer scenario. But in normal applications, I never use either software flow control or hardware flow control. But I do remember I use it for my internet, my Wi-Fi, for my internet cards. So when I want to transfer data to my internet cards, then I will request to send, then it will reply with CTS. If that is clear, then it give me the allow me to transfer the data. Okay? So that I remember I use hardware flow. I did use the control flow in my applications. I never use software flow control in my application, just in my study. Okay? And then the asynchronous communication data format. So first we need to know the structure of data frame. So we have a start bit, indicate the beginning of data packets. Right, data bits is for data being transmitted, typically from 5 to 9, and commonly 7 or 8 bits. Optional parity used for error detections, and stop bit one or most bit. So we can see the as in the figure, right? We have idle, start, and then start with bit 0, bit 1, bit 2, repeat, and then parity, stop, and idle. Okay. So after the line goes, the stop bit is received, the line goes to an idle state, right? Normally logic high. Then we can start another transmissions of data. But in synchronous, the structure is a bit structure of data format is a bit complicated. We have clock signal, synchronized communication. Used to synchronize the communication requires an signal of set clock. The clock synchronizes the data transmission and receptions, right? Ensuring both and read and write data at the same time. So data transmitted continuous stream, we don't start and stop bit. Yeah. In the synchronous, we don't have that frame. Synchronous byte. We use in some protocols and synchronized byte or words exchange lines to transmitter. So sometimes we call it as we have the preamble, right? Preamble, and then we send the data. So the preamble consists of the sometimes the address of the receiver, and then the number of data, right? The number of data that we're going to transmit, maybe 2 byte we use for that, and then at the end, then we have the for the post-amble, or sometimes called end of the transmission, end of EOC, end of communication. We, maybe inside it we put the error detections code or error correction code. Right? So that's the way how the data in transmissions, synchronous transmission is being packed. Being packed. So for the reason that the synchronous data is data communication is more efficient. The data rate is higher compared to the asynchronous. So here you can see that there are two different data format. The start and stop bit asynchronous requires start and stop bit. Synchronous communication doesn't pay this bits due to the set clock. And then clock signal synchronous relies on accurate baud rates, and synchronous on use an external or set clock to synchronize data transmissions. Change the detail of the data frame. So basic structure of the synchronous data frame, the clock signal, crucial part of synchronous communication. It acts as timing difference for that synchronous data transfer between the transmitter and receiver. And then data frame component synchronization or preamble is often a specific byte or sequence of byte sent at the beginning of the transmission. The purpose of this preamble is to alert the receiver and prepare it to read the incoming data. It's line receiver clock with the transmitter timing. Data payload, the main part of the data frame that contains the actual data. So the actual data is called as data payload. Then optional checksum or CRC, sometimes we use checksum or use some synchronous communication protocol includes error detection mechanism at the end of the data frame to ensure data integrity, and then post-amble used to some protocol as a sequence to mark the end of the data frame, saying that the transmission is complete, and so on. Okay, so we can see the frame of synchronous data consists of the preamble data and then the post-amble, right, which include the checksum or or CRC or the whatever others that important for that data transmissions. This is detailed example of synchronous data frame. So you have the preamble, data byte 1, data byte 2, carry on up to data byte 9, n, sorry. Then we conclude with the CRC and checksum. Right, okay. In case like Manchester encoding and so on. Okay. Receiver rate is data bit at precise clock edges, right? Rising or falling edge. Example protocol with synchronized frame. Well, we have the SPICE example protocol. SPICE serial people interface uses clock line along with data lines, mostly visual. Data is transferred in sync with clock and no start and stop bit are needed. I2C in pass mode, while I2C is often considered semi-synchronous to its king network. We will cover all this later on, right? SDCL, higher level data link control. We have flag, address, then control, then data, FCS, and then we have the flags. So that is the some protocol line. Advantage of synchronous data frame, higher data rates, precise timing, continuous data flow. Disadvantage complexity, of course, and very more lines are needed, right? Because of to transfer the clock signal. And then we talk about error data detection and correction data transmissions. So error data detections, we have in general we have 4 methods, right? Parity check, a simple technique that add parity bits. You detect a single bit error but fail for multiple bit error, right? Checksum, the data is divided into blocks and their sum is calculated. Offer modulo a fixed number, modulo 10 only. The sum is appended to the data for verification at the receiver's end. And the other technique that we have is a cyclic redundancy check or CRC, a polynomial-based method that generates a checksum by dividing the data by a predetermined polynomial. CRC is highly reliable for detecting burst error. And the last one, humming distance, measure the difference between two binary strings to detect error based on their expressions in binary space. These ones I never use and we not cover it later on. We will cover parity check, checksum, CRC in detail, not humming distance. And then we have error corrections. Even we're not going to cover it because it's not suitable for it's not used in the simple basics embedded system programming, but it's used in such applications of satellite communications. So, but I just list down here humming codes, add redundant bits to the humming popular in signal processing. This guy, this is technique to data to enable single bit error detection and correction. Use parity bits strategically placed in data stream, and then we have a read Solomon code, right? A block code that can detect and correct multiple error in a block of data, widely used in CD, DVDs, and QR codes. Port error corrections, FEC, redundant data is added to the transmitted message so the receiver can correct error without needing a retransmissions. Convolutional codes encode data as the sequence of overlapping block to provide error correction. Commonly used in digital communication system like 4G LTE. Okay, it's not our area. Automatic repeat request combines error detection with retransmission request. If an error is detected, receiver request is sent to retransmit the data. Error detection and correction is very critical, right? In the techniques, fundamentals in maintaining seamless and error-free data transmissions. But we just focus on the commonly used error detection methods, as the other method is really used in the embedded programming system programming, right? Students are encouraged to consult comprehensive resources like computer network Networking and Internet, editions by Fred Hassel, the book that I use while I study data communications. Very good books. Now we talk in detail of the priority bit. The priority bit is one of the simplest methods for error detections. It involves appending a single bit known as a priority bit to a data set. Right? Actually, we can have even parity and odd parity, as you know, right? So examples here, we have 10100001. Usually we have 3 ones, so the priority bits ones. So if you use the we use the even parity, so it should be 0, because the parity becomes 0 because it contains only 3 ones, right? 3 ones or odd ones. But if you use the odd scheme, then the parity bits must be 1. Advantage simplicity, of course. Low overhead method add only single bit add to the data, 1/8, for example, right? Limited error detections. So if 2 change, you cannot detect, right? Cannot detect. If 1 or odd, then you can detect. There is an error in the data. But if more than, if it's happen even, you cannot. Error cancellation is failed to detect multi-bit error. Not multi-bit error. What I can see here is it can detect even change of data or bits. How is work? The transmitter calculate the priority bit based on the data being sent, then it append the data before transmission. At the receiver, then it will calculate the parity based on the received data, then including the parity bits. If the recalculating priority does not match the transmitted priority or the mutual open scheme, parity scheme used, then an error is detected. This is example of parity bits generations, right? So you can see here, calculate parity bits equal to 0 because 4 ones. That's already already bit even. Transmitted data 1000, then add with 0 at the back. This incorrect. This incorrect. Actually, should be 110101 0 and then add with 1, because if you use the even parity, because the number of 1 in the original data is even, Okay, so this example of codes, functions to calculate it. So just call it, then it will. Another another thing that we have is checksum. Checksum usually we just have the basically we have the number of data. Say we have 7 data, right? 7 data. Then we pump the data inside it. We add all the data. We call modulo 2 and modulo 10 binary additions. Actually, what is modulo 10 is just the additions without taking the overflow or the carry out, right? Say the data bit is 8, we just take only the 8 bit of the result, right? That is modulo 10 binary additions. Then we invert it and add 1 or to form the 2 complements. In other words, actually checksum is the negative of sum of the sum of the data. Okay? So advantage simple to implement fast minimal computations. Limitations is not robust. And then basic error is suitable for simple data integrity checks, but not recommended for application needing high reliability. That is checksum. So this is example of the checksum, right? So we have 85, 170, 204. Add all of them. Actually, we got 11001011 carry out 1, but that overflow we take out, we not consider, right? We not consider it. Okay. Then we form the second complements, and then we transmit the data 1, 2, 3, the data, and then we add it with the checksum. At the receiving, we add all of them. The expected result should be 0, right? If not 0, there is something wrong in the data. Again, we are using both. We are using the the summation of data. We are using the modulo 10 binary addition. All right, next we go to the cyclic redundancy check, or CRC. This is widely used error detection. I use it in the checksum. I use it in the wait. I use it in DHT11 and 22, right? 22. DHT22, DHT11, I use the CRC. In no, I use checksum. For the what we call that one, the what accelerometer. Accelerometer we use the checksum, and then for the light intensity sensor, I use the CRC, and then in the what we call the RFID, I use a CRC. So a CRC is widely used. So it uses a polynomial that is agreed upon polynomial, and then we will calculate the what we call the what CRC based on that polynomial. So it depends, right? It depends on the device, right? Sometimes it is no, it depends on the device. So need to read the data sheet, right? Sometimes the device can calculate. You just feed in the data to the device, then the device can calculate for you the CRC. So this example of calculation of the CRC. So we have 8-bit data 10111001. Right? Use a 4-bit generator for email x3 power 3 plus x1 plus x0. So for that, because we have x power 3, so we need to add at the back of the data, 30, because the power is 3 of 3. Then we divide it with the polynomial generator, which is 1011. 1011 is come from the x power 3, and then x power 2, then 1 power x power 1, then 1 power x power of 0. So in binary it is 1011. Divide it all along to get the remainder. Okay? So the remainder actually is the CRC. Add to the data frame and transmit it. So when we receive it, what we do then, we again add all of them and divide all of them, okay, with the open agree polynomial 1011. Then it should resulting in 0. Else the data is an error. Okay. So that's example of the code implemented in C. Next, we talk about the data communication equipment and data terminal equipment. What is data terminal equipment? Data terminal equipment is the actually the data that we use, the data communications is what, the data that's data communication. the data terminal actually, for example, we use the modem, that is data terminal. Data terminal, no, that microprocessor, computer, and data communication is a modem and so on. So, okay, the first one we see, this is the data terminal, to data terminal, data communications or DC connection at LPTTL, low power TTL, 3.3 volt, or TTL level 3 volt, right? Then sometimes we use the data terminal, we connect both them through the line driver. We can use the popular standard RS232, right? RS232, recommended standard 232. And later we discuss about it. Okay, data terminal, data sources or data. Okay, data terminal is data sources or data sink in a communication system. So, example, computers, yeah, terminals, routers, and microcontroller system. And then data communication equipment is facilitates data transmission between DTE. For example, modems, switches, network interface devices, whatever lah, GPS, GSM, GSM, and so on. That is the DCE. Normally we use the RS232 interface, right? Why RS232 interface? Because of the RS232, we increase the noise margin, right? Noise margin of the lower TTL level, yeah. Normally TTL is about at the noise margin about 0.4, 0.4 volt, or if we talk about the CMOS sometimes it depends. If at 5 volt the noise is around 0. Wait, 0.3 0.3 of VDD. So for 5 volt it is about 1.5. But with the RS232, then we increase the noise margin. However, the ambiguous or indeterminate range for the RS232 is between -3 volt to 3 volt, right? -3 volt to 3 volt, as shown there. And then minus 15 volt is the minus is we can say as 1 or mark, and then positive we can it is 0 or space, right? Distance for RS232 can go up to 15 meters at lower speed, right? So if you use say 15 meters, maybe, so reduce the baud rates, right? The bauds maybe around 2,400, right? But if just about 1 meter, you can speed up to 2,000, 4,000, 200,000 or 400,000 bit per second. And then the other one that we have is the pin out for DB9 connector of the DTE and DCE connections. But here I just show you the hardware flow control connections for DTE to DCE. So we have RTS to CTS, and then CTS to RTS, then ground to ground, of course, common ground. And then, of course, then remember TX will go to RX of each of them. And we can consider another RS standard that we have. We have RS 485 and so on, right? So that once we have or in automotive we have controller access network, CAN controller access network. And when we talk about because we are going to use the STM, So I just show you the block diagram of the USART, the USART of the STM. So on top we have the transmit and receive block from the. So whenever we transmit data, data from the data in parallel, push into the transmit receive register. So that transmit receive register, we convert it into serial and push it into transmit data register, and that transmit data register will go to the lines, to the lines, right? To the lines. Okay. Then whenever receive, that data will be converted into this to the parallel through the C4 serial in, parallel out, right? Parallel in, parallel out. So change to the parallel data, right? And then here we have the baud rate clock, BRR register, right? That control the baud rate of the USART, right? And I think the block diagram is not too, right? No need for us to memorize it, right? Just understand a bit how it's working, right? Because now everything can be configured by using the STM Cube MX. Uh, the most important thing in the embedded systems for when we talk about data transmissions is the methods. The first method that we have is polling methods. In polling methods, the processor continuously monitors a flag or register to check the status of data transmission or session. So it will wait for transmitting. It will wait until the data completely transmits, or it will, and then during for receiving, it will wait until it got the flag that say the data is received. It's waiting there, right? I mean, this is simple to implement, useful for system, but I don't think that it is simple. It's difficult sometimes. Disadvantage is if it's inefficient as a processor to start in a loop, wasting time and energy. Poor performance in multitasking system, of course, because it's stuck there, waiting for the data to be transmit or waiting data to be received. In interrupt mode, then the processor perform the task while waiting for interrupt signal. So while doing something, if you transmit the signal, then it will check if the line is free, then it will transmit the data. Right? Whenever transmit interrupt in the interval, right, the first byte, then the data will be transmitted, right? Then the interrupt service routine we trigger, right? If we trigger the interrupts to transmit the next byte, then we just the processor through the interrupt, right? We transmit all the data. In receiving too, same. While doing things, then if the data comes in, then it will trigger the processor to read the data in. Advantage efficient as a processor is free to perform other tasks while waiting for interrupt, or suitable for system with multitasking or high data rates. Require interrupt handling codes which can add complexity, I don't know. May introduce interrupt latency if multiple interrupt occurs. Yes. So we need to set priority correctly, priority of interrupt correctly when we working with the interrupt mode. Direct memory access means now we are using another controller, looks like a controller, to control to transfer the data, right? To transfer the data. So that's the difference between the interrupt modes and the direct memory access, right? So highly efficient as the CPU is free, data transfer ideal for large data block and high speed data transmission. Disadvantage more complex configuration compared to polling or interrupt mode. Yes, not suitable for small data transfer due to overhead. Idle mode, and the last one that we have is idle mode. In idle mode, the processor waits for data reception without performing tasks continuously, often used in conjunction with what to detect inactivity or receiving line. So I don't want actually when transmitting, we just transmit just like a normal either use GMA. Normally I use GMA to transmit the data, transmit it. But idle mode is clear when we talk about receiving. See, when I transmit the signal, I receive the signal, saya suka makan nasi. Saya suka makan nasi. So, it's trigger when I receive, saya, S-A-Y-A, saya suka makan nasi. Then after that is going to idle, right? So when it's going to idle mode state, then you will trigger the interrupt. So idle mode, right? Idle mode here referring to the idle data. Right? Idle data. The data is idle. So this is something wrong here. I will rewrite it, right? Rewrite it, and I will show you the code later on. Actually, the code is in serial COM 3, serial COM 3 for idle mode, serial COM 1 for the for interrupt, and then serial COM 2 for DMA with interrupt mode. So we can see that in methods polling, interrupt, DMA with interrupt, moderates is low, idle mode low, complexity high, complexity is high, detecting inactivity of or end of data. The complexity is high for idle mode. That's a bit wrong. So each method has its trade-off and choice depending on application requirements, system resources, and data rates. We will explore all these techniques in the next video presentation slides. So please, please, watch all the video about the data communications or USART, right? USART in polling, USART in interrupt, USART through DMA, USART in idle mode. That's all from me. More, please register to UniKL British Mission Institute. Bye bye.